Hey there, my name is Francie Wharton. I'm from Skidmore College, and this summer I was a part of the CLASSE REU at Cornell University. Here at CLASSE, I've been working as a part of TIME. TIME stands for Tomographic Ionized Carbon Mapping Experiment. Basically, TIME is an instrument that will be going inside of a telescope at Kitt Peak in Tucson, Arizona. This instrument will be used to study the early universe, specifically the time when the earliest stars began to form. At TIME, we measure the emissions from these early stars to determine how they came to be and how these emissions kicked off a period in cosmic history called the Epoch of Reionization, otherwise known as the EOR. In the very early days of the universe, the gas that filled it was not evenly distributed. The pockets of high-density gas collapsed in on themselves, and that is what created the very first stars. These stars began to emit ionizing radiation, which then reionized the surrounding neutral universe. This period is what we call the EOR. At TIME, we want to study the EOR because so much is unknown about that period. Scientists have lots of questions on how the process began and how long it took. TIME measures the emission lines of a gas called singly ionized carbon, or C2. This gas is specifically found in areas of high star formation. So, by tracking where the C2 is, we're able to easily see where reionization occurred. In order to do this, we use very sensitive detectors called TES, Transition Edge Sensor Bolometers. These detectors act like little thermometers. When the emission line hits the detector, it heats it up, and we use that change in temperature to indicate the strength of the emission line. This temperature change is so small, so we have to keep our detectors very cold. Specifically 250 millikelvin. We do this using a device called a cryostat. A huge part of our job right now is learning how the detectors work and how well the detectors work. We do this by shining a known signal that we call the reference signal into the full detector array. Then we compare that to what the detectors actually pick up, which we call the detector signal. If we know what the signal we put in looks like, then we can easily tell if the detectors are doing a good job at showing us what they're seeing. We do this kind of testing with a device called a beam mapper. The beam mapper has a signal on a motor. We code the motor to move in XY space in front of the full detector array. This allows us to hit every single detector. When each detector is triggered or heated up, we're able to record the position that the beam mapper device was at, as well as the intensity of the signal picked up by that detector. We call that term the amplitude. My job this summer was to write code that would turn all of that beam mapper data into plots to make it easier to understand. Those plots look like this. You can see here that it is brightest when the signal is underneath the detector, and then as the signal moves away, the brightness begins to drop off. Once we are sure that the detectors are doing a good job showing the reference signal from the beam mapper, then we can move on to known signals from space, like planets. If the detector images the planet correctly, then we know we have made a successful detector array, and we can start to measure unknown sources from space, like the EOR. Overall, I'd love to thank everybody involved in the CLASSE REU. I learned so much this summer and really enjoyed being able to work in a professional lab setting at Cornell. I especially loved all the hands-on work I got to do with the cryostat this summer. Thank you so much again. Have a great day.